But what are the states? What are the possible states? And the way we determine that is based on these electrons right here, the valence electrons. Now, you might be tempted to remove this 3d3 because it goes in the end. But this 3d3 actually has less energy than the 4s2. The 4s2 is actually slightly farther out, and so it's going to get removed first. So we can think about this as removing electrons by orbital. Okay, so if we remove a 4s2, and I'm just going to write this in the NLX form here, 4s2, 3d3. If we remove that 4s2, then we end up with just 3d3. We're now deficient 2 electrons. That means that vanadium can have a +2 charge. Now, it can also lose the 3d3 electrons as well, but it can't lose the 3d3 electrons unless it loses the 4s2 electrons, because these are higher energy. And so vanadium could also exhibit a +2 +3 state. So that means that it's +2 and actually +5 because of combining these 2 electrons. Okay? So the possible oxidation states for vanadium are +2 and +5. All right. Now things get a little bit more tricky with copper, and I picked copper in particular because it's a little bit tricky. So these are, let me just box that. So those are the possible oxidation states. So with copper it gets a little bit tricky, and some of the metals around that area get a little bit tricky, and I will show you why in just a second. Well, I mean right now. I'll show you why right now because that's what we're doing. So copper is right here. Okay, so it's basically the entire electron configuration that we just said, but it's to here. All right, so it is, again, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Now 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9. 3d9. Now the thing about the d orbital is that it actually does not normally stably exist in this form. It doesn't stably exist when it's that close to being full. So what normally happens, and I'm just going to switch to the abbreviated form, so don't be alarmed. So what actually happens is we end up with a 4s1 and 3d10, because this is more stable. Okay? So this is more stable than having 4s2 and 3d9. And that's because the d orbital is slightly lower in energy, so it takes that valence electron and it steals that valence electron, and then it comes from that s orbital. So if we're talking about oxidation state, what do we have to consider? We have to consider the fact that, again, we can lose our 4 electrons, or sorry, our 2 electrons. So we can lose this 1 electron, or we could lose 10. Now, losing 10 is not very common, so this will probably not be lost. And so that's why I will not cross it out. And so the only possible oxidation state is a copper that is deficient in 1 electron. That means that the only possible oxidation state is +1. Now we know based on copper 2 that that's not true. So this one's a little bit of a weird exception. But using this technique, we determined that the oxidation state is only 1. In reality, there are other reasons that allow copper to have that oxidation state. All right. For chromium, for the last one, chromium is over, let's see where chromium is. Chromium's over here. And so this is another exception, or rather weird anomaly, I guess, if you want to call it that. So 1s2, 2s2, 2p6, 3s2, and these are all in the same row, right? So that's why I'm just doing 3p6, 4s2. Okay, and so now we're at the D block. So oh man, I dropped something there. So chromium's there, so that's 4. So that's going to be 3d4. All right. So if we abbreviate again to the NLX form, have argon, 4s2, 3d4. Now again, this d orbital will steal an electron, and that's because it's almost half full, because it likes to be half full, right? It's stable in that half full form. So we end up again with argon 4s1, 3d5. Okay. And so in this case, because it's not completely full, I can get rid of this one, and we can probably get rid of that one too. And so we'll end up with chromium plus and chromium plus 6. And this is actually, I think, a normally observed state of chromium. So the possible oxidation states are +1 and +6 based on the electron configuration. Again, there are a lot of reasons that can allow these metals to have different oxidation states than we've determined here. However, this is the way to do it based on that electron configuration. Okay, so that is determining oxidation states and electrons. Okay, let's move on. So now we're going to do some ranking by electronegativity. Okay, so we're going to rank each of these atoms by electronegativity, and at the 15-minute mark right now, so it's going to be a bit of a long video, but hopefully we can get through everything. So we're going to rank everything by electronegativity, and what we need to do that is the periodic table. So let's consider what trends we're talking about. What the trend we're talking about in electronegativity is this trend, right? It's a trend that says that as you go this way in the periodic table, things become more electronegative. So let's look at what that means. Okay. So we have oxygen, fluorine, nitrogen, chlorine, iodine, arsenic. Okay, so if we can put these maybe side by side, might be better. If we put these side by side like this, like that. I'm not sure if this part of it is visible right now or not.